For people who don't know me, I'm Alek. I also actually started fairly recently here after spending a bunch of time in MSR New York, and today I'm going to talk about a line of work we started in the New York City lab, thinking about a lot of sample complexity issues in reinforcement learning, and some thoughts about how to address it. So just to set some ground concepts, we'll talk through what reinforcement learning is through a very basic example. We have this rat that's sitting in a maze. It can see what it sees, and it can take actions in this environment by moving from one place to another, and maybe at some point it stumbles into the piece of cheese, and depending on whether it likes the cheese or not, it gets a positive or negative reward. So there's a few things I want to call out in this very simple example that are very important, right? So one aspect that's crucial to most reinforcement learning problems is that of exploration. When it starts out in the environment, the rat has absolutely no idea about the layout of the maze, that there's a piece of cheese even sitting anywhere in the environment. It just has to sort of explore its surroundings and figure out what might happen through interaction. And it has to do that really kind of over a long sequence of steps. Like initially, when it stumbles around, it gets, maybe apart from banging its head or something, if it walks into a wall, there is no real signal saying moving in one direction is better or worse than moving in another direction. So there is no necessarily immediate quality signal. And finally, it kind of needs to generalize across related observations, right? So when it maybe perceives a wall once and bangs its head, and maybe does it a second time, but unless it learns pretty quickly that, okay, banging head into wall is bad, I should not try this for every wall I see, it's going to end up with a very sore head. So there is sort of this obvious need to generalize across related observations, because we'll have a lot of unique observations that we might make. So that's all pretty standard. Now let's think about how reinforcement learning is usually approached. And there's a bit of a divide in how this is usually done currently in empirical and theoretical lines of work. So empirically, I'm sure everybody in this room has seen something about all of the reinforcement learning that's going on in games, in Atari and Go, and Miss Pac-Man, and in various such settings, and largely being driven by progress in deep learning. So much so that deep reinforcement learning is now a well-defined thing. And what's kind of the main driver of this line of work is that we are this generalization problem of the rat being able to reason across similar observations. That's being done really well because these neural networks are learning very interesting representations of the problem space that allow us to generalize across them very effectively. But usually we are doing relatively simple forms of exploration in most of the empirical works, with few exceptions. So that's kind of where a lot of the empirical work is currently going on. And for theory, I mean, people have been doing theory in reinforcement learning for a while now. It's not a new thing, right? But and there's a pretty rich literature that deals with this exploration question. That it's actually one of the most interesting questions that has been studied carefully, but to a large degree in small state MDPs. So if you give me kind of a grid where there are only maybe 10 unique states, then I can tell you how to explore, and there are amazingly efficient exploration algorithms in that setting. But they can't extend to like the agent perceiving the environment as a rich image or as a rich audio or text or anything like that, right? So there's kind of an obvious opportunity when you see that gap to think about how do we develop approaches that can address that can perceive the environment like this, but have the types of efficient exploration guarantees that were developed for small state MDPs. And that's the question driving the research that I'll be talking about today. And we study the reinforcement learning problem in a pretty broad setting, which subsumes a lot of other formalisms that you might have seen before, that you might be familiar with. And the upshot of studying a fairly general setting is that we end up getting conclusions for many different classical models that people are used to. But for simplicity, it'll be useful to just focus on Markov decision processes for the most part. And we'll think of Markov decision process with really large state spaces. So the number of states doesn't have to be 10, but we will rely on some structure in that state space, as will become clear. And just in a nutshell, what I'll describe is a new way of thinking about what makes a reinforcement learning easy or hard from the perspective of exploration. Right, so just like in supervised learning, like in classification and regression, we can ask what makes a classification problem easier or harder, and we have notions such as VC dimension, for instance, that try to answer this question. What are characteristics of a problem that make it easy or hard for exploration? And we'll show an algorithm whose sample complexity does scale with this measure, and because our algorithm is developed in a very general setting, it will have implications in various specific models. But unfortunately, the algorithm is very far from practical at the moment. I'll talk about that towards the end. Okay, so let's start with the model, right? So hopefully most people are familiar with MDPs, but just real quick, so you have some initial distribution over states. You see a state, you take an action, and you get to see some instantaneous reward. Also, based on your action, you transition to a new state. Note that here we're going to assume that the process is Markovian, so the next state only depends on my current state and action, and my reward only depends on my current state. We'll also make a couple of additional assumptions. We'll say that the process is what's called episodic. So basically, you repeat these transitions for h steps for some fixed quantity h that's known to everybody, and then it ends. So you can think like, okay, you'll maybe run the game for a certain number of turns and then end, or you'll like think about having a conversational agent that goes no more than like 10 turns in a dialogue or something like that, right? So this is called an episodic MDP, and just for simplicity, we'll think that the set of states that can be observed at each at time step 2 and time step 1 are distinct. So that's just to avoid some terrible clutter in notation if I don't assume that. Okay, but the key challenge I want to take here is I do want to allow a large number of unique states that the agent perceives. So even though I'm drawing this as a little grid, I really don't mean that the number of states is small. Okay, so what's the usual objective in RL? We want to maximize the reward the agent picks up. And the agent is obviously going to act according to some policy. So what's a policy? It's just a mapping from state to action. And okay, so let's think about when we are thinking about large state MDPs, what are examples of settings we might hope to capture? So grid world is probably it's been the poster child of reinforcement learning examples for a long time. So you have an agent in a grid, and it can move in any direction, and maybe there's a goal state where you get a reward. If you die by falling into the lava or something, then you get a negative reward, right? So that's kind of the view of the world on the left, and that's been the classical view of RL. Of course, maybe the more modern view of RL is that the agent has some head-mounted sensors, and it's perceiving the world through the 3D image it's observing, and your problem hasn't changed, but now the observations you perceive and consequently the complexity of your policy might be considerably larger. Of course, it need not have anything to do with agents and mazes and so on. We can think about very different problems such as even session level optimization in web search as a reinforcement learning problem where our actions would correspond to search results and our states would be the queries and information we have about the user and so on. Okay, so what do we know about MDP, or what do we know about finding policies that give us high reward? That's our goal, right? So what we know is, if I want to find a policy that is no more than epsilon suboptimal, so that the reward it will give me is at most epsilon worse than the largest reward I can get, then I need roughly this many samples. That's the prediction of classical RL theory. Oh shit, my mouse is, oh, there it is, good. Right, so, okay, so it is some reasonable polynomial in number of actions in the problem horizon in 1 over epsilon. These are all pretty usual and not too bad. The thing that really hurts us is this cardinality of the state space. That's that shows up in the usual results. So that says inherently that if we have a problem with a small number of states, we are okay. A problem with a large number of states, we are going to require a lot of data. It is just not. It's not the case that we have this result because people obtaining these results were lazy and didn't work harder to get a better result or something. There's actually a fundamental limitation here in that if you really have a problem with a large state space, the amount of data you might require fundamentally, no matter how smart you are in designing your algorithm, can be very large. So in particular, there is a problem with an exponentially large state space where the amount of data will really be exponentially large. So if you don't a priori control the number of unique states or put some other structure over the state space, you are in trouble. And you're in trouble because, again, like for these types of things, we are usually still stuck in that grid view of the world, right? That we are thinking about each state as a unique entity, whereas when we have a lot of states, we really want to reason across them. We want to rely on some structure between them, and we want to generalize across similar states based on that structure. So this is the generalization bit that's missing from a lot of existing exploration algorithms. And the most common approach in RL to do this is by a technique called value function approximation for generalizing across states. So let's go into that a little bit. Oh, by the way, if there are any questions at any point, feel free to interrupt me, please. Okay, so what are value functions? So the intuition for value functions I like best is in terms of a function that takes a graph and tells you shortest paths in the graph from given a position, right? So what is Q? So Q, it's usually value functions are denoted as Q, and Q star is the value function of an optimal policy. So what these Q functions do is they take a state and an action and tell you something about the long-term reward if you act optimally, right? So you're at state X. Suppose you take action A at this step, but after that you act optimally. Then what's the total reward you'll experience? So for instance, if you were thinking about shortest paths, you're saying maybe in your current state you take one step to the left, and after that if you take the shortest path to the door because you're really bored of this talk, then how many steps do you need to exit the room? Now these functions are really useful because if you tell me the shortest path length from all my neighboring states, then how do I find the shortest path from here? I just go to whichever neighbor promises me the shortest path. Yes?
Quick question. Is the optimal value function something you know in advance, or?
No, it's just a concept right now.
I see.
Right, so we're defining something, and if we had this thing, it's useful because basically we can just act greedily according to this function, and that's an optimal policy. So it's a very useful object to have if you have it. Yes?
Maybe negative of the shortest path, right?
Sorry?
Negative or 1 over the length of the shortest path. So that this automatically.
Yeah, so I'm kind of fudging between rewards and costs in the, yes, thanks. Or maybe you want the longest path, the scenic route to the door.
Is the reason why it's useful because once you have it, you just don't need anything but to follow the function?
Exactly. So it eliminates the need to think about the long-term nature of the problem, right? You're just like at every step you're being greedy with respect to it, and that's it. So a very sort of natural way a machine learning person might think then is, okay, so if this Qstar is really so helpful, maybe I just collect a bunch of data and find a function which looks the most like Qstar from that data. And how do I do that? I'll just I'll commit to my favorite family of functions. If you were doing research in early 2000, that would mean that you take linear functions. Currently, you take neural networks, but you take your favorite family of functions. You pretend that one of them is a good approximation to Qstar, and you just try to fit some data in order to discover which one of the functions in your class that is. Okay, so we'll do the same thing. We'll assume that there is some family of functions we have. These functions have same semantics as Q functions, so they take in a state action, output a real number. We'll also equip each function with its greedy policy. We know the greedy policy of Qstar is the optimal policy, so we'll also keep the greedy policy of each f around, right? And we'll use function classes that we know kind of generalize well across similar examples. So linear functions, for instance, we know again from like doing linear classification and regression, generalize well across examples. Similarly for neural nets and decision trees and so on, right? So we'll just sort of rely on what we know from supervised learning in some sense. Okay, so that kind of really starts to suggest some basic template of an algorithm, really. I start with some initial guess for Qstar. So that guess f1, it will have some greedy policy associated with it. I collect some data from that policy. And now somehow I want to use this data to improve my guess, right? To obtain a better estimate. And then I can just iterate this process if I could do that. So this sketch would work if I knew how to, given maybe such data, how to obtain a better estimate, right? But that's not obvious how to do that, because it's not like I can collect samples which are labeled according to Qstar, for instance. If I could do that, then my job would be done. Any questions so far? Okay. So now, since we are trying to discover something that behaves as Qstar, maybe we can look at some structural properties of Qstar and verify them on the data that we've collected. And one such structural property is called a Bellman equation. Again, it's useful to just think of our shortest path analogy here. So if I tell you the shortest path to the door from here, and I take a step, then my shortest path should only change, either increase or decrease by 1. Or, right, it should not change by more than 1. If it did, then I was either lying at my old position or new position. So same thing here. We're saying if you said I get a certain long-term value in a certain state action, and I observe the instantaneous reward for this state action, then I transition to some future, and I ask you again, how much do you think I can get? Right? The difference between these two, if you're not lying, should be 0, the difference between these three quantities. Because this is your promise about my future, and this is your present prediction. And this is going to be 0 no matter which state action pair I ask you about. Right? It should really be true, sort of in a very point-wise sense. Because, and just again, we can think about our shorter path situation. It's going to be true at every position that my answer is always self-consistent with my answer at one step to the left or right. Okay? So basically, I have these equations that we know Q star would satisfy no matter what XA pair I ask this question about. Since I can ask this question at every XA pair, I can also ask this question under any distribution over XA pairs. And so I'll use this notation where pi is describing the distribution I have over the X's in particular, over the states. So think of pi as a policy that you took some number of steps according to that implicitly puts you into some distribution over the states. And then you'll verify this one-step consistency. And because I know this one-step consistency should hold if f was Q star, maybe this is a check I can use. So I'll collect some data according to some pi maybe. I will verify whether the error is 0 on that pi. If not, then I have found a witness that you cannot be Q star, and I will declare you illegal as a candidate for Q star. Right. So that's one thing we'll try to use for our algorithm. We'll say, okay, so I'll just maintain I'll maintain a huge profile of policies, which is in this case just the greedy policies of all my value functions in the class. I will make sure that you have 0 Bellman error for each and every one of those policies. If not, you'll be thrown out. The trouble is even verifying for a given candidate f whether all of these errors are 0 or non-zero is statistically pretty challenging because you have a large collection of policies. The number of policies here is still the same as the number of value functions in my class. So if I were to take f1 and collect data according to its policy, and then f2 and collect data according to its policy, and so on to check these equations for even one function, I would require too much data. And that kind of is what drives a lot of the negative results that we know about the sample complexity. And the problem is we basically have too many functions, and a priori we don't know, we still haven't put any structure over the problem, right? So without any structural assumptions, there is no reason that data that you collect from one policy can be used to check the Bellman equations for another policy or something. So let's try to introduce some structure into the problem now. Okay. So what I do is I construct this this matrix. This is going to be a really large matrix. It's going to be indexed by functions f and g on the 2 dimensions. So f is a candidate for being Q star, so is g. I look at the Bellman error of f under the policy of g. Okay, so I'll do this for all fg pairs. This gives me a huge matrix. Now I will ask, what is the rank of this matrix? It turns out the rank of this matrix is often small, even though this matrix is huge. So for instance, if you did give me your 10-state MDP from the classical RL, I still have a lot of, usually they work with, if you have 10 states, they would still, they would still work with something that's, and you have k actions that's like 10 to the k in terms of the cardinality of f. So you still have a very large function class, and so you still have a very large matrix, but you can show that the rank of this matrix is no larger than the number of states. You can actually start, now this is kind of a cheap one in some sense because we already know how to handle a small number of states. And we get to see what the number of states is. But this matrix can have a rank that also depends on the latent properties of the process. So for instance, if you have a very large state space, but the transition matrix of your MDP has a very small rank, then it turns out to be another valid upper bound on the Bellman rank. Andre?
In general, the class f, set f, I think it's uncountably infinite, right? So do these results
They extend. They extend. So you can think of it as a linear operator. That's or okay. The easy way is you can think of basically taking your infinite thing. You can construct an epsilon net of it, and then now you have a discrete thing. You can apply this, and you like the approximation errors can be dealt with.
And so it doesn't have to be compact, for instance. Set F.
Compact in the topological sense or some other
Yes.
sense?
Yeah.
Well, here it is discrete.
Yeah, but in general, if it's infinite, like, does it have to be compact for these results to carry over, or?
Well, it has to have small complexity in a certain sense. So, for instance, it has to have something like a VC dimension bounded. So an analog of VC dimension for regression should be small. That doesn't necessarily relate to topological compactness directly. It's a more combinatorial notion, so I can't really say necessarily.
It's okay. We can.
Yeah. Okay, but the important thing is that, like, unlike the number of states in an MDP, the Bellman rank is not something you get to see. It's latent in the process. So, for instance, you can even take a POMDP, which is kind of our poster child for a latent variable RL model, and you can show that the Bellman rank is bounded by the number of hidden states as long as your policies and value functions are being reactive. So they only depend on the most recent observation. If they depend on the last 10 observations, then you'll get like hidden state to the 10 or something. So it depends on how far you have to look back in history. But the cool thing is that it's relying on sort of the intrinsic structure of the problem, not just the explicitly declared structure of the problem. Right, so you can with sort of that intuition, what you can, very crude way you can think about it is, if your agent perceives the world like this, but this view was an okay approximation for all the, for the value functions and policies and so on, then the Bellman rank will depend on the number of cells in this grid, even though your agent will actually continue to act in this world. So it's something implicit.
In the 3D world, is partial observable, right?
Yes. So well, you'll have to take some history along with you, but that's okay. As long as the history is not terribly large, it will still be fine. So I'm not saying again, like, yes, formally I said let's think about everything as an MDP, but in the paper we are allowing everything to be partially observable. There is no Markovianness being assumed. Other questions? Okay. So, in the interest of time, I'm actually going to skip over. Okay, so where are we so far? So I've said at this class of functions, I'm assuming my problem has a small Bellman rank. Now I want to find a function in this class that satisfies all the Bellman equations, and actually it turns out that there's going to be lots of functions that will satisfy all the Bellman equations, because these are not the standard Bellman optimality equations which have a unique solution. These are weaker than that. So a lot of functions from your class might satisfy them. And we want to find, amongst those, we are still looking for one that gives us a useful policy, a policy with a high reward. Now the intuition we want to exploit is that this Bellman rank of the matrix is telling us that there exists, in some sense, a lot of structure in this matrix, and ideally I would like to use that structure for efficient exploration, because it's saying that there are kind of just a few directions in which you can, if you can get information, you learn everything about the matrix, which means you learn kind of about all the different policies. You can reason about all the different policies by just a few observations. But at the same time, that structure is hidden to us because we just know that the matrix has a low rank. We don't know what a factorization of the matrix is. So we have to still discover that. So that leads to the algorithm. It's an optimistic algorithm, like most exploration algorithms in RL. One of the things I like about RL is how optimistic we are. So So, and it's an iterative algorithm, so it kind of, basically it's, to some degree, it makes a guess, it does some checking, and then it does a bunch of elimination. Andre?
So by the rank of the transition matrix, you mean the rank of the highest. So each action has a transition matrix. So it's the rank of the highest ranked action.
Yeah.
Question. This seems to apply to a particular state space. Any sort of a statement or guarantees that if you take the same objective function or system of rewards to a different state space, so let's say the maze is different, that will help out at all, or you just need to start from scratch again?
So this is in the most vanilla RL setting where you just have a particular state space and in fact a particular transition process and so on that you're acting within. So yes, if you change that, you'll be learning from scratch.
I see.
How to sort of transfer across related problems and so on is something people look at, but that's not what I'm talking about today.
Okay.
Yeah. Okay. So about the algorithm. So the algorithm is iterative. It's going to basically first make an optimistic claim. So what it will do is, so we have some initial state distribution. Let's just think of actually the initial state as being unique. So we have some initial state. It asks each function f, how much value, how much reward do you think I can get if I follow your action starting all the way from the initial state. So I'll just follow your greedy policy throughout. How much reward do you think I'm going to get? And I'll just take whoever promises me the largest reward, right? I'm feeling optimistic, I'll just trust their claim. Now, this is actually useful because what you can show is that if you happen to stumble on the Qstar function here, then this will actually be the value of the optimal policy. So if somebody is claiming something large here, they are hopefully claiming at least as much as the value of the optimal policy. Okay, but I'm not going to be completely naive. I trusted this function, so I'm actually going to verify this optimistic claim now. So I will take the greedy policy corresponding to this FT. I will execute it in my MDP a bunch of times, and I will say, well, does my Monte Carlo estimate agree with the value I was promised? If it agrees, I'm actually quite happy because, like I said, one of these functions is actually Q star. So whoever was optimistic here is promising me at least as large as Q star, and they delivered on that. So I'm done. I can return the policy. And if not, it turns out you can show that FT has a non-zero Bellman error on data collected with policy pi t. So that requires a proof. That's not obvious, but it can be shown. So first of all, we have found evidence that FT is not Q star. It has Bellman errors. So we'll toss FT out. It turns out with slightly clever bookkeeping, you can also toss out all other functions which may have non-zero Bellman error under this policy pi t that we just executed. So we toss out basically a bunch of functions, and we restrict our value function set to be the ones which are not tossed out, and we repeat this iteration, and each time we do this check, this maximization, restricted to the functions that were not pruned. Okay, so we know we'd reduce the set by at least one each time. Well, it turns out we actually reduce the set by a lot each time, so much so that the process terminates pretty fast. So overall, what we can show is that if Q star was one of the functions in your set, and if the Bellman rank of your problem is no greater than m, then you'll find a near optimal policy, a policy which has reward at most epsilon less than highest in these many trajectories. So for people who have seen these types of results before, for classical MDPs, usually you get something very similar, except there is a dependence on number of states here. So that's kind of the upshot of all of this, that we've taken the place where number of states used to appear and replaced this with a much more general notion, which is this Bellman rank. But it also tells us that in some sense, so Bellman rank might be like a nice way of generalizing the notion of number of states. And there is some additional thing that pops out, which is a usual way of thinking about complexity of a finite function class in learning settings. So here, if you were going from a finite to infinite class, for instance, you might have something VC dimension like pop up. Yeah.
If you go to the previous slide, Alec, here it feels like the initial data you have for choosing that optimistic estimate has a lot of influence on your state space. For example, if some rare but important states where, let's say, some disastrous things are happening are never represented in that initial data that you have, the policy you're going to be, like, I'm talking about actually the bias in that initial data that you're going to be saying.
So the initial data is coming from the initial state distribution, right?
So you're assuming kind of a sampling from the true distribution of the world in a way that even these rare states with disastrous situations.
Well, so I'm thinking of an episodic process, right? So episodic process, there is always some distribution over the start state, and then with that distribution over the start state, then everything unrolls according to the transition distribution based on your actions. But there is always some fixed distribution over start states that you begin with, because otherwise, well, you can either do that, or we have to then talk about kind of the V star of a particular state when you start from that state. Like you do one or the other usually. Right?
But at the end of the day, when you really implement this algorithm for real, somebody is going to give you a sample with limited size.
Yeah.
It's not going to be infinite.
Yeah.
And I'm talking about the setting where there are some important states, but there are really rare in that distribution. But
well, so are we thinking of at least the sample being representative of the distribution or not?
That's my question, because I feel like for this to converge to the right thing, there is that underlying assumption that your initial sample is actually good representation.
But that's true almost. That's true even for supervised learning, right? If I give you a sample that is not a good representative of the distribution on which you'll be asked to predict later on, then all bets are off.
I'm just wondering about the convergence properties, because it feels like where you converge really depends on the properties of the initial space.
Well, everything is, right? So, the optimal policy, the optimal value function, they will all crucially depend on the initial state distribution. So definitely, yes, where you converge to is very heavily reliant on the initial state distribution. And it's true in a certain sense that, like, we are applying this optimism only under the initial state distribution. So in some sense, if like you have a policy class where something catastrophic, like later on, has a very little effect that trickles up to the initial state distribution, then that can cause problems. But yeah, this is at least this is, I think, at least a reasonable question to ask in. So I would say what you're asking is maybe an interesting kind of perturbation or robustness question we can ask on top of what's being studied here. And yeah, that's an interesting way to look at it. Adit?
So following HS thing, so when we say we are collecting trajectories using the policy,
yeah,
So I'm also worrying that there are some policies for which you just very rarely hit the rare state, so we actually need to collect a lot of trajectories to get the Monte Carlo approximation error small enough or large enough.
Yeah, so that's kind of where like your epsilons kind of really help you. So because you are, yes, if in some sense, if I only wanted the optimal policy and nothing but the optimal policy, then what you're saying would be correct. Like what happens here is that if you, so here I'm accepting if you violate your optimistic contract by up to epsilon, right? What you can show is that if you violate it by at least epsilon, then there's at least an epsilon probability with which you will hit some state that I don't know about before, some state that is unknown to me yet. And if you visit some state with at least epsilon probability, then I know 1 over epsilon many trajectories will give me a good number of visits to that state. And so that's actually that's important for the sample complexity to stay tractable.
So in general, to distill the result, suppose you have a fixed initial state, or equivalent of the fixed initial state distribution. It's part of the problem specification. You know the transition function, so you can compute this expectation exactly.
Yeah.
Okay. So if under these conditions given enough computational power, and assuming that f is set of all tables, tabular functions is going to converge to the optimal policy.
Correct.
Right?
Correct.
Okay.
Yes. So if there are no approximations everywhere, anywhere, and you have the set of all functions, this will find the optimal policy. Okay. And so that's kind of the first point here, that if you go back to the small state MDP where you're working with a set of all policies, then it will imply the same sort of sample efficiency guarantees that were proved in late 90s, early 2000s, and so on. Except it's not necessarily going to give you the best results one can get in those settings. We are definitely not able to capture the most sophisticated arguments that can be done there in our general setting. But it does yield actually new results in several settings for which basically nothing existed before. So that's kind of the main upshot of the result. And the nice thing is that because you're getting everything through a common lens, so you have kind of a good unifying treatment for several threads of sample efficient RL. Okay, so I'm going to skip over this. So far I've talked about sample efficiency. What about actually implementing the algorithm? Turns out to be a nightmare. So every iteration of the algorithm requires basically solving a constrained optimization problem. We are trying to find the function promising the highest value, subject to a bunch of equations, right? We are saying, oh, sorry, this should have been subject to this thing equal to 0 for all previous data collection policies and at all the different levels h. And it's this set of constraints is pretty nasty. So non-convex in F, well, that's only a problem for people like me. I know there are people who are very brave about non-convexity these days, but actually, even if you are kind of cavalier about it, usually non-convexity in an objective is much more tolerable than non-convexity in the constraints like it sits here, and most people even in non-convex optimization land kind of get some jitters when you have non-convex constraints. And here it's non-convex and non-smooth, in fact. The other thing is that we can show that even for very simple problems, there are MDPs where actually this optimization problem is going to be NP hard to solve. So that's kind of really annoying. I know how to solve tabular RL problems in statistical and computationally efficient manner, but this particular algorithm will not solve it in computationally efficient manner. So that's kind of a price we are paying for trying to come up with something that works more generally, that it actually can be kind of annoying even in simple cases. So those are some negative results we proved, and it made us incredibly sad. Okay, so on that sad note, I'll talk in a moment about where kind of there's room for progress. But I think the thing that's kind of interesting is we are identifying a new structural condition on reinforcement learning problems that describes when can efficient exploration be done, and that's something that in a way beyond like having a small number of states, we didn't have very many results about before. So it's really a fairly new type of result. We make a bunch of modeling assumptions, and almost all of them we are fairly robust to. So the paper talks about basically how to add robustness to just about every assumption we make. I'll talk a little bit about the future directions. So I think the biggest, I've been worrying about this for over a year now, how to make this damn thing computationally efficient. One thing is, of course, we can start piling on more assumptions, right? So, okay, we can take a version of this problem with where the transition dynamics are fully deterministic, and then it turns out we can change the algorithm a little bit and things become computationally efficient. We can try to think of this really, can we explicitly try to reconstruct the factorization, maybe at least in POMDP-like settings, where the factorization really depends on the hidden state. So can I just solve that latent variable model somehow? And that's kind of something we're working on right now with an intern. But more generally, this is all about value-based reinforcement learning, right? There are other flavors of reinforcement learning. What about model-based learning? Actually, I'm kind of excited about a new work in progress we have going on again with one of the interns. We're getting some interesting results that extend what we have here to model-based settings and try to understand when can using a model be better than using just value functions, when can it be sort of complementary, and there's going to be some good stuff in there that I'm excited about. And then there is so that's kind of asking what is more than value-based RL. There is also what's less than value-based RL, which is just somebody gives me policies and I want to find a good one. And there I'm pretty stumped. And how to think about sample efficiency, in particular because a lot of the techniques here relied on off-policy reasoning. So it's not so obvious how to do how to extend the sample efficiency theory to policy search procedures. But thanks for your time. There's two papers on which these results were based. The sample efficiency result and the algorithm comes from the first paper, and then the hardness result and advances in the deterministic case are in the second paper. Happy to take more questions. Okay.
So if you added back Markovianness, the assumption of Markovianness, stationarity, and removed the finite horizon, so you would introduce a discount. Would NP hard? Would it still be NP hard? Would the algorithm be still as inefficient, or you could tighten up? Well,
I have to think about it.
Like if you were solving basically a discounted reward MDP, no.
Given that I haven't worked out all the details even of the algorithm in the discounted reward setting, I do not want to give a conjecture right now whether the hardness result stays or not. It probably, okay, so I think stationarity might be a problem.
You did not assume stationarity in this work, right?
Well, in finite horizon, it would be weird to assume stationarity. But no. So I don't think the specific construction we have for hardness will work in a stationary setting. I'm less, but at the same time, I don't know how to actually do anything better with the algorithm itself even under those assumptions. So we try to do like a lot of variants of the algorithm. So I mean, one thing that you would really like to do in, for instance, stationary discounted reward problems is you would like to set up some sort of a dynamic programming type maybe thing, right? And well, the only thing that changes in the episodic setting is that you're going to do it back to front, the dynamic programming. But we were always finding that accumulating errors were creating a lot of problem, accumulating bias in particular. So that's why algorithmically I don't see how to use the assumption, but I don't know if the hardness result carries over.
Just I would think that this algorithm would reduce the policy iteration. if you
well, no, it's at least using value functions, right?
Well, policy iteration also makes sense.
Sure. No, well, so where would the elimination aspect get captured?
Well, in policy iteration, you're in a sense also eliminating certain things. Well, certain tables.
But
actually, now that I'm thinking about it, policy iteration is exponential in the number of iterations in the worst case.
Exactly.
That's not a good idea.
So have you looked at the pseudo-compute paper from Mark Bellman?
Pseudo-compute? Yeah.
Paper, yeah.
Yeah.
How do you think it relates to this? Because they also, I mean, they try to come up with a sort of account-based thing such that you can also, their goal seems to be similar.
Their goal is definitely similar. So they're trying to do sample efficient exploration, and I don't know. My answer is if you're in a problem where you have a density model good enough that those pseudo counts are a good enough approximation to real counts, you're lucky, good for you. I mean, somebody basically, in some sense, solved the state abstraction problem for you, right? They're effectively, you can roughly, like the way I think about it is that that's roughly equivalent to telling me that if I take, I don't know, the level sets of the density function you gave me and think of them basically as like mega states, that's going to be a good enough tabularization of my process. And so certainly they've constructed a good density model like that for Atari, and whenever, yes, we have something like that, that's fantastic, but it's not obvious how to do it. Actually, with one of the interns who's working on like a more POMDP style approach, we're trying to compare with pseudo counts, except we are not trying to run our method in Atari, and that's creating a lot of problem because how do I apply pseudo count? There is no agreed upon. So it's, yeah, I mean it's assuming something, it's expecting something more from the problem, I guess, is, and if you have that, great. So, but there's definitely been a couple of interesting approaches like that from the empirical side towards also exploration, right? So there is the pseudo count, there is also like the curiosity-driven thing from Berkeley and so on. So I think it's nice. It's an important problem. It's good that both sort of theorists and practitioners are making their own attempts towards the problem. Hopefully, we'll find something that we all agree upon is a good idea, and that'd be nice. All right.